Here's problem number 11, 13. A solid sphere, radius r, mass m, rolls without slipping down an incline as shown in the figure. The linear acceleration of its center of mass is... Let's consider this as being a torque about some pivot point, which is the contact of the object with the incline. And our torque is going to be the component of gravity that's going down the incline, which we know to be mg sine theta, and that's being applied at a distance of radius r about the pivot point. So our net torque about this object is going to be equal to that force times that moment arm, and that is going to be equal to mg sine theta times r. That is our net torque about the pivot point. Sounds good? If we're going to consider this pivot point, we need to calculate the moment of inertia about that pivot point as well. Our moment of inertia is going to be equal to the moment of inertia of the center of mass plus md squared, where d is the distance that we moved the pivot from the center of mass by the parallel axis theorem. So this is going to be equal to the moment of inertia of the center of mass plus mr squared in this case, because our d is actually equal to r. Our d is this distance that we moved the axis from the center of mass. Okay, we're doing this in a general way, so we can put any moment of inertia of the center of mass in there. In particular, for a sphere, this is going to be 2/5 mr squared when we come down to it. Alright, so our net torque is equal to the moment of inertia times the angular acceleration. And this should be true in general. And our net torque, as we calculate it, is mg sine theta times r. And that is equal to the moment of inertia, which is the moment of inertia of the center of mass, plus mr squared times the angular acceleration alpha. Alright, let's factor out a mr squared on the right term, and we have that mg r sine theta is equal to the moment of inertia about the center of mass divided by mr squared plus 1, all that times mr squared times alpha. Well, the m's cancel out on both sides of this equation, and one of the r's cancel out. So we have an r gone here, and the square of the r there gone. And we can recognize that alpha times r, which is left over here, is really the linear acceleration a. So what we have here, left over here, is that g sine theta is equal to the moment of inertia by the center of mass divided by mr squared plus 1 times the linear acceleration a. Or the linear acceleration is equal to g sine theta divided by 1 plus the moment of inertia about the center of mass divided by mr squared. That's our result in general for a rolling object going down the incline. We can use this for several problems yet to come. But in this case, we know that the moment of inertia about the center of mass is indeed 2/5 mr squared. So we can go one step further, and we can say that this is equal to g sine theta over 1 plus 2/5 mr squared over mr squared. The mr squares cancel out. 1 plus 2/5 is 7/5. So this is equal to g sine theta over 7/5 or 5/7 g sine theta for the sphere. So that's our answer. 5/7 g sine theta is the linear acceleration of this sphere going down the incline. But we're going to be using this equation that we derived in general for the following problems.